Welcome back, everybody. So we've been going down this journey of integrating rational functions, so polynomials divided by polynomials. And we saw last time that our first tool is to use long division if we have an improper kind of fraction, which doesn't mean it misbehaves or it's a bad fraction. What it means is that the degree of the numerator is bigger than or equal to the degree of the denominator. Just like we would take, say, 5/3 and divide it, go ahead and divide the 3 into the 5 and make it 1 plus 2/3, right? That's what long division lets us do and gets us a simpler fraction to deal with, one where the degree in the top is less than the degree in the bottom. So throughout the next little bit, we're going to assume we have already done any long division if it was necessary, and what we have now is sort of a proper rational function, one where the degree in the top is less than the degree in the bottom. So here's an example of that kind of rational function. So if we want to integrate, say, 3x minus 2, that's nice and linear, over, well, I'm going ahead and factored it because that's going to be the first step in these, is to go ahead and factor the denominator. And it factored into x plus 2 and x minus 1. Of course, that's a quadratic in the denominator. If I multiplied it out, you'd see it started out x squared. So the degree in the top is definitely smaller than the degree in the bottom. We're good to go. Now, the partial fractions trick here is a really cool trick. And again, there's absolutely no calculus here. This is not calculus at all. This is just algebra. It's just kind of complicated and ugly in places, algebra, but it's really just algebra. In fact, when you stop and think about it, it's algebra that that you may have wondered why we never learned this before. In other words, when you were first doing algebra, pushing symbols around, solving for x's and all this sort of stuff, well, the first things you had to do was add fractions and get common denominators. And so what we're doing is just the reverse. What we're doing is we're just uncommon denominatoring. Right? So what we're going to do is take this fraction that looks like it's been put together with a common denominator, and I'm going to bust it up into two fractions, right? Where we've lost our common denominator. Okay? So in other words, I'm going to break this up into a number over the x plus 2 plus a number over the x minus 1. We'll call those numbers a and b. And the process of doing that, of breaking up these fractions, this fraction into two different fractions like this. In other words, the process of uncommon denominatoring, right, is what we call partial fractions. So if I were going to take these a over x plus 2 and the b over x minus 1 and combine them, right, recommon denominator them to get what I have on the left, the 3x minus 2 in the numerator, then what I'd have to do is get a common denominator, multiply the first fraction by x minus 1, the top and bottom, take the second fraction, multiply it by x plus 2 in the top and bottom, and when I put them together, when I recommon denominated this right-hand side, I'd get something like this. Now, I'm not going to go through all of this step every time because, well, A, it's really boring, and B, you'll quickly see how to get to where we're going without writing this down every time. But I think it's important to see where it is we're going to get this, what we're really doing. And it's really just, well, we're trying to uncommon denominator this original rational function. So the way I'm going to do that is imagine that I already have split it up, and what would happen if I put them back together? Well, I'd get all of this. Now, the cool thing is all of this, right, with the A's and the B's, should be equal to, well, the thing I started with. And if you stare at that for a second, you go, oh, wait a minute, look, the denominators are the same in both of these fractions. So the really cool thing is the numerators would have to be the same. So we get this really awesome equation. And from now on, we'll just skip straight to this step. We won't write down the denominators part because the point is the denominators will always be the same. So what we do is we start with the a over x plus 2 and the b over x minus 1, and we put those back together as though we were recombining them to get a common denominator and set that equal to the denominator that we're supposed to have, the 3x minus 2. Oh, that makes sense? Otherwise, it seems a little bit like magic as to where these terms came from. But the equation that we get, that's what it's all about right there, this sort of fundamental equation. Right? Well, now what? Well, if you remember back to high school algebra, you may have remembered solving systems of equations where you'd have like two equations and two unknowns. And here I've got two unknowns, an a and a b. The x, I don't know what it is either, but it's really the a and the b that I care about, right? When I'm done, I'm going to stick those into my integral, and x will still be a variable. So it's really only the a and the b are the variables that I care about right now. But I've only had one equation. Well, okay, I hit the button and now I have two. Where did this second equation came from? I went ahead and I collected like terms. So if you see here, if I take the a, distribute it through the x minus 1, that'd give me an ax and a negative a. Over here I'd have a bx and a plus 2b. And if I collect like terms, then say with the constants, I'll have a negative a and a 2b. So negative a and 2b. Feels like Hamlet. Negative a and 2b, or not 2b. Then for the x's, I'll have an ax, I'll have a bx. So I could go ahead and just factor the x out of that. See, this is ax plus bx. But if I go ahead and factor the x out, then this looks like a plus b x's. And then here's my constants, and here's my original numerator, the 3x minus 2. So why in the world would I do something like that? Well, now you see, how many x's do I have on the left-hand side? I've got a plus b of them. How many x's do I have on the right-hand side? I've got 3 of them. And the first time I saw this absolutely freaked me out. I had no idea what the teacher was talking about. I thought this is the craziest thing I've ever seen in my life. You know, what do you mean? But now that I've taught it, of course, it makes perfectly good sense to me. And hopefully this will start to make some sense to you. You'll think of it as counting up the number of x's on each side of the equation. So on the left, there's a plus b of them. On the right, there's 3 of them. So that actually gives me an equation. I know that whatever a and b are, a plus b has got to equal 3, because the number of x's on the left and the right have to be the same. Okay, well, that's all well and good with the x's, but you can still play the same game with just the plain old numbers. See, what plain old number do I have on the left that doesn't even have an x with it? Well, that's negative a plus 2b. On the right, the plain old numbers turn out to be negative 2. So whatever a and b are, negative a plus 2b has to be the same as negative 2. Okay? So now I have two equations, and now I've got two unknowns, the a and the b, and I can set about doing whatever way of solving systems of equations that you liked in high school to figure out what the a and the b are. So here are my equations again. If I clear the screen, my favorite way of doing something like this, these are usually pretty simple compared to really, really long examples you might have seen before in high school. This one in particular is pretty easy because notice there's an a and a minus a. So the obvious thing to do here would be to do elimination, to add these two equations and eliminate the a. If you don't like that and you want to solve this using substitution, knock yourself out. If you get really ambitious and you decide you want to write down a matrix and row reduce a matrix, knock yourself out. Remember though, you won't have a calculator on the exam, so the numbers will be picked so that they all work out nicely like this example does. So you might want to think of how would I solve this without a calculator. So what I would do here, of course, is add these two equations. That means that the a and the minus a will cancel. The b and the 2b would be not 2b anymore. It'd be 3b. And the 3 and the negative 2 gives me 1. So now b has to equal a third. 1 divided by 3. Now as soon as I know what b is, I can substitute that back into one of the equations. Either one, the top one's probably the easiest one. So a plus a third, because that's what b is, a plus a third has to equal 3. That's my first equation. Then I take the third to the other side. I have to do a little arithmetic with fractions. Again, that's not that bad, and doing this much arithmetic with fractions would not be unreasonable on an exam, say. So I'd turn the 3 into 9 thirds. Take the 1/3 to the other side. When I subtract, I get 8 thirds for A. So again, this fractions, yeah, you have to be careful, but it's not hard. It's just being really careful. And notice there's no calculus. This is awesome. This is just algebra. Okay? So now that I know what A and B are, I can substitute that in. And so what I have done is uncommon denominatored my fraction. I've busted that joker up into two separate fractions. 8 thirds over x plus 2 and 1/3 over x minus 1. Of course, if you wanted to check your work, and again, you would probably have enough time on the exam, you could do the algebra to put those back together and check and see that, sure enough, that if you got a common denominator and put those back together, you would get what we started with. So awesome. But the cool thing about this is even better. This is super easy to integrate, right? 1 over x plus 2, well, that's just going to give me a log. The same for the 1 over x minus 1. The numbers, the 8 thirds and the 1/3, I can just pull out in front. So I get 8 thirds log of absolute value of x plus 2. Don't forget the absolute value. That's really important. Then plus the 1/3 of the log of absolute value of x minus 1 plus my friend the c. Don't want to forget the c. So this is a typical straightforward sort of example with nice easy numbers and an easy example in that we had two linear factors, right? On the exam, you'd expect to see numbers that maybe turn out to be fractions, but that aren't so bad you can't do them without a calculator. Polynomials that will factor reasonably nicely. I wouldn't give you a cubic to factor because that can be really, really difficult if you don't have a good guess at what one of the factors are. But quadratics to factor, that sort of thing, unless I guess the cubic, you could factor out an x and make it a quadratic. All the numbers should work nicely. But what's going on here is just algebra, right? This is part of what makes this so awesome. Okay, let me show you another way of finding the A's and the B's in this example. I said that if I were doing this, I would have done, what I did. Actually, I probably wouldn't have done it the way I did it. I would have done a cuter trick here called the Heaviside method. So let's go back to that original equation where we're solving for the A and the B. And of course, we know what A and B are, right? They turned out to be 1/3 and 8 thirds. But let's try getting them a different way. You may never have seen this before. I know I had never seen this before. And I know the first time I saw this, I thought the teacher was smoking something. I thought, yeah, she's really, really, really on something good here to come up with this idea. And it wasn't until, of course, I had seen much more advanced math that I realized what it was that was really going on and why this works. Well, I can tell you some of the real reasons for why this works. Because this equation is true no matter what the x is, right? All I really care about is A and B. But no matter what x is, that equation's still got to be true, right? I mean, I'm solving for the A and the B, but it's got to be true for all x's. So what I can do is just plug in a few x's and see what happens. Like if I stuck in 1 for x, you see what'll happen. Sometimes they'll call this striking factors because as soon as I put a 1 right there for x, this 1 minus 1, oh wow, that's 0. Everybody see that? So all of a sudden, 0 times a, well, that's easy to deal with. The a went away. You think, oh wait, what happened? You killed my a. No! Well, that's okay because what was left was just 3 times b equals to 3 times 1 minus 2 is just 1. In other words, I got rid of the a's and I had an equation left with just b, which is awesome because I could solve that and figure out that b has to be 1/3. And that's great because, well, we knew that b was 1/3, which is convenient, but also this was much easier to do the algebra, right? I didn't have to combine like terms and go through all that. So if you can do this, this is a really clever and cool way to make this work. I'll show you another way, another number to plug in. What would I plug in to try to figure out what a is? In other words, what could I plug in that would get rid of the b? Well, it'd be -2, right? Because as soon as I plug -2 into here for x, then the -2 plus 2 will give me 0. The b part goes away, right? And this leaves me with an equation with just a's in it, which is great because I can solve this and get that a has to be 8/3. So the Heaviside method looks really weird. I mean, when I first saw this, I thought there is no way this can possibly work. But it does, and the reason is this equation that we've gotten has to be true no matter what the x is. Anytime you plug an x in, um, this equation should still be true. And so we can plug in different x's, and if we plug in the right x's, we get simpler equations that we can use to find our a and our b. So very, very, very cool stuff. Let's try another example. So here's one with, again, this is susceptible to the partial fraction process because it's a quadratic on top, 2x squared plus some stuff, over a cubic on the bottom, the x cubed. So it's a proper fraction. We can't do long division. It's already been long divided. It's a degree 2 over a degree 3, ready for the partial fraction process. So, okay, let's go ahead and factor the denominator. So pull that x out so it's factored. And then let's try to bust it up and an uncommon denominator it. I mean, you'll notice that this is as factored as it's going to get because the x squared plus 4 is what we call an irreducible quadratic. Okay, so here's 10 seconds of a pet peeve of mine. Actually, it's not irreducible. What it is, it's irreducible using real numbers. You could factor it and break it up, but it'd have to break up into x plus 2i, remember square root of minus 1i, and x minus 2i. And for lots of irritating reasons, calculus books try scrupulously to avoid using complex numbers, which always irritates me because my research is essentially calculus kinds of stuff with complex numbers. So this actually becomes a lot easier if you just go ahead and factor it using complex numbers. And the arithmetic is actually much easier than what we're going to do here. But every calculus book in the world brushes over the complex numbers part. They just use real numbers, and it makes the algebra uglier, but that's what they all do. So that's what we'll do here. But end of my rant that complex numbers are better in the way to go. So what do we do here? Well, I need to break this up. So an x in the denominator and an x squared plus 4 in the denominator. Now, you'll notice that when I wrote this here on the screen, I've got a blue a over the x, but the x squared plus 4 has a bx plus c on top of that. So why the difference? Why not just a b? Right? Well, the answer is it's because the bottom is an x squared plus 4, not just an x plus 4. In other words, the bottom was a quadratic, so what goes on top of it is a linear function, a bx plus c. I haven't even attempted to give you any rules to decide what you put over what and how all that works. And I'm not going to now. I'm just going to tell you this is the way that we want to set it up to make it work. And in a few minutes, I will explain, or probably in the next video, why we put what over what, where the B's and the C's come from, and how we decide to break it up. But for right now, let's just go through the process of how you would find the A's, B's, and C's and what we would do with it when we find it so that we see the how this works. And then we'll learn, I think in the next video, why we picked the A's and over one term and the BX plus C over the other. So if I were going to put these back together, right, if I were going to take these terms and recombine them, I'd end up with what I started with. So what I would have to do is multiply the a over x, well, top and bottom by x squared plus 4. So that would give me a times x squared plus 4. And this part would have to get multiplied top and the bottom by x. So I'll end up with a times the x squared plus 4 plus the bx plus c. It gets multiplied by x. So I've gone ahead and multiplied through here to make it bx squared plus cx. That would be the numerator, right, of my recombined terms here. And of course, I know what the numerator should be. It should be the numerator I had when I started. It should be 2x squared minus x plus 4. So sometimes people think that what I'm doing here is cross multiplying. I'm not. In fact, we'll see an example in the next video where it's obvious that that's definitely not what I'm doing. I'm not cross multiplying, even though it kind of looks like it. What I'm really doing is multiplying the a by whatever I would need to recommon denominator and get back to what I started with, and multiplying the bx plus c by whatever I would need, in this case an x, to recommon denominator this and get back to what I started with. I'm not just cross multiplying. More about that later. So now I've got this equation, right? A times x squared plus 4 plus bx squared plus cx plus 2x squared minus x plus 4. Great. So the problem here is Heaviside. I mean, we're going to do it, right? Because Heaviside is cool and it will work. It just isn't as much good because if I plug in 0, that'll be great. I can get rid of the b and the c in one fell swoop. If I plug in 0, the x squared and the x will both be 0. That'll be gone. I can use that to solve for a. But there is no real number I can plug in to get rid of the x squared plus 4, right? The right numbers to plug in to get rid of x squared plus 4 are plus and minus 2i. So what we'll do is do this the harder way with real numbers. So I'll plug in x equals 0. I mean, may as well do that while we're here. This is actually really cool and really quick. The b times x squared plus c times x is just 0, right? The x squared plus 4 just becomes 4. So the entire left-hand side of my equation just becomes 4a plus 0. That's awesome, right? And the right-hand side is even better. I mean, 2x squared, that's 0. Minus x, that's 0. It just leaves me with a 4 on the right-hand side. So a is just 4 divided by 4, just 1. So plugging in 0, that knocked out the b and the c, gave me an equation with just an a. Awesome. I know what a has to be really, really easily. Problem is, what do I do next, right? If I plug in any other number, I can't get rid of the a. So I'm not going to. What I'm going to do is I'm just going to pick an easy number to plug in and just hope that the algebra works out okay. So the next easy number other than 0 is probably 1. So if I plug in 1, well, it's not as good as 0, but it's not bad. I'll have 1 squared plus 4 times the 1. Where did this 1 come from? Well, the blue 1 right there, I already knew that's a, right? And it was 1 to begin with. So I'm just plugging in numbers into here. And since I already know what a is, because that was easy to find, I'll go ahead and use that. So my blue a is 1, then 1 squared plus 4, b times 1 squared plus c times 1. That just gives me b plus c. And on the right-hand side, this is 2 times 1 squared minus 1 plus 4. All that together gives me 5. So altogether, this turns into, well, b plus c plus 5 equals 5. The 5's cancel, so b plus c has to be 0. Okay, so this is 0 again. That's cool. What's the next easiest number to deal with other than 0 and 1? Well, you might try 2. 2's not a bad number. I think I'm going to go with -1 because, that's smaller than, gives me smaller numbers than dealing with 2. Although you could do 2, that would also work. Any number you want to plug in here will work in the sense of giving us an equation. I just want to use, I could plug in 17 million. It would work. It'd give me an equation. But I will be an ugly equation with nasty numbers. I won't make this easy. I want to use nice, easy numbers. So the easiest number for me to plug in is probably -1. Because what will happen now is I'll have 1, again, that's because that's a, right? Then -1 squared plus 4 plus b times -1 squared, okay, that's just b, plus c times -1, oh, the negative there actually matters. It makes it -c. Then on the right-hand side, when I plug in -1, there'll be 2 times -1 squared minus -1 plus 4. You do the arithmetic, all that turns out to be 7. So I have, well, 5 plus b minus c equals 7. If I take the 5 to the other side, I get b minus c equals 2, doing all that arithmetic. Okay, well, that's not so bad. I mean, I've turned this into 2 fairly simple equations with 2 unknowns, so I can just solve those. And what I would do is add the 2 equations just like we did before. In this case, the plus c and the minus c are going to cancel and give me 2b equals 2, so b would have to be 1. Right? If I know b is equal to 1, then I can just go ahead and plug that in because I know b plus c equals 0. So 1 plus c equals 0, or c has to be minus 1. So not too bad, but it didn't work as nicely as it would have had I not had that irreducible quadratic term. When I have linear terms, the Heaviside method just lets you breeze through it without much trouble at all. When you have an irreducible quadratic, this is still what I would do, but you have to work a little harder because we still get a system of equations with a couple of variables and a couple of equations that we'll have to fight with, but not too bad. The other way to do this is to collect like terms, right? This is the way we did it the very, very first time when we tried that last example. So what we would do is go through and collect all of our x squareds and all of our x's and so forth. That's not too bad here either. So let's collect all of our x squareds. So I have ax squareds, I have bx squareds. So altogether I would have a plus b x squareds. Then I'd have a times a 4, right? So that's my one constant over here. I have a c times x, that's a c times x over here, and that's it. Everything's all collected. The x squareds are collected, the x's are collected, the constants are collected, all together. And then the right-hand side, everything's nice and laid out, easy to see. So I go through the same process we do before and say, how many x squareds do I have on the left? There's a plus b of them. How many do I have on the right? There's 2 of them. So whatever a and b are, a plus b has got to be 2. Otherwise, I'd not have the right number of x squareds on either side. Same idea. What about the c's? There's cx on the left. There's negative 1x on the right. So, oh, look at that. C has to be negative 1. That's awesome. That equation's already solved. We're good to go. The next one's almost as easy. The constants over here, just plain numbers, 4a on the left and 4 on the right. So 4a has to be 4, so of course a has to be 1. Now, once I know that much, I can go to the equation with the a plus b equals 2. And so that says 1 plus b equals 2, so b has to be 1. So that's actually maybe a little quicker than doing the Heaviside method this time. Either way works. You can do it however you want to, as long as you do it correctly when you do it. I like the Heaviside method, and that's probably what I would do because I think it's really cool and I'm used to doing it now. But collecting like terms this way also works fine. So with all of this drama and carrying on trying to figure out what our A's and B's and C's are, we finally have them. A is 1, B is 1, C is minus 1. Wow, it was a lot of work for for a bunch of ones and a minus 1 here. But this is cool because now our integral becomes really, really, really easy. And again, notice we haven't done any calculus. All we've done is algebra. Again, long, painful algebra, but this is just algebra. So we end up with 1 over x, right? A over x is 1 over x. That's easy, right? It's going to give me a log. Now, the second part is the one that's a little trickier. This is x minus 1 over x squared plus 4. Now, that's the one that gives people, well, an unfortunately large amount of trouble. Because if you have a quadratic in the bottom, then, and depending on what the top looks like, then it may be that this is really easy and you can just look at it and it's just really, really easy. Usually it's not. Usually the best way to do it when you get to this point is to go ahead and split this up. So in other words, this is x minus 1 in the numerator. Let's just go ahead and bust that thing up so that it's x over the x squared plus 4 and negative 1 over the x squared plus 4. It looks like I've made it worse, right? I mean, why did you, you know, they had a common denominator. Why did you decommon denominator them again here, right? To break up the bx in one piece and the c in the other. The reason is it's actually much easier to integrate. So the 1 over x, that's just going to give me a log of absolute value. Don't forget the absolute value. The next piece in that red box there, the x over x squared plus 4, if you stare at it, that's a u substitution problem. If you let u equal this denominator, x squared plus 4, the derivative of x squared plus 4 is 2x. And look, I've got an x sitting out there. So I do u substitution. I let u equal x squared plus 4. The du would be 2x, so I'll have to put in a half. And when I integrate that, I'll get log. Remember, it'll be 1 over u. So I'll get log of u, or absolute value of u. So 1 half log absolute value of x squared plus 4, just from this second box. That integral is not too hard, and it's actually very different than what I'm going to get from the second box. Because from the second box, I don't have that extra x. I just have a negative 1 there. And you look at this for a little while and go, oh, wait a minute. That's an inverse tangent. This is 1 over x squared plus a squared, where the a is 2, right? So 2 squared is 4. So this is the formula, or we can hit it with the formula for inverse tangent. Remember, that's 1 over a inverse tangent of x over a. So the a here is a half, because that's, remember, x squared plus a squared. The a is 2. So I'll have minus, this minus 1 gives me a minus sign, then 1 half inverse tangent of x over 2 plus c. So the moral of the story here is we want to take our proper, with the degree of the numerator smaller than the degree of the denominator, rational function, uncommon denominator it using this partial fractions process. And when we're done, we'll get something that's much easier to integrate. You have to be a little careful sometimes if you have an irreducible quadratic to go ahead and break that up even further if you can, and split it up to the point that you can integrate each piece.